heat, momentum, and mass, and find a relationship between them. And the way that we can do that is through okay. So we can relate heat, momentum, and mass through the concentration. And we can further explain concentration by diffusion and diffusivity. We can explain the concentration by diffusivity. And we can relate those topics. We find that all of them will have a diffusivity of meters squared per second. So let's start off with one thing that we already know. Let's start off by looking at momentum. And one of the ways that we can examine momentum as a flux analogy is the idea, okay, and one of the ways that we can figure out this relationship is through a flux analogy. And this is the idea of a physical property and heat, momentum, mass, even fluids, how they move through a type of matter, a subject, a substance. So for anything, it will be how far, and you can think of area by how long. And this is just a general idea, just to get you thinking. So let's first look at momentum. We can momentum through the shear stress equation. It is shown as the viscosity multiplied by the shear rate. And we can further break it down by showing the types of units that we have. So this will be represented as force per area. So momentum flux is equal to viscosity times the volume, or times the velocity in the x direction. And one way that we can relate this all together is by going and multiplying and manipulating the equation by the density. And so density is in units of kilograms per meters cubed. So if we were to break down the rest of these, if we want to multiply the rate, so the velocity, we can multiply by the density. In turn, that means that we have to divide by the density for the viscosity in order to make it cancel out onto the other side. So in turn, we get an equation that looks like this. Viscosity divided by density times the rate or velocity multiplied by the density. And now breaking this down by units is how we're going to be able to find some kind of relationship. So if we take a look at the shear stress rate, we have velocity is in meters per second, and then multiplied by the density, which is kilograms per meters cubed. When they cancel out, you are left with kilograms per meters squared per second. Okay, and if we want to take a look here, we see that this kilograms meters divided by second is the units for momentum. And then meters cubed is volume. Which in turn, this will mean we have our, and this will be our concentration gradient. Okay, now let's take a look at viscosity divided by density. So viscosity is kilograms divided by meters per second. When you divide, you have to multiply by the reciprocal. So that will be meters cubed per kilogram. And once you do some canceling out, you are left with meters squared per second. And this is going to be our diffusivity for momentum. Notice this is the correct units of meters squared per second. So let's go back to our equation that we had here. If we relate it back to the idea of flux, we have the diffusivity is going to be how far, sorry, that's going to be how long. And you can think of that in terms of time because we have the meters squared per second. And then we are going to have the concentration gradient is how far. So let's write that out. Okay, so now that we've worked with something that we already know, momentum. Let's try to relate it back to heat. So for heat, we can still use another equation to find that meter squared per second. We are going to use Fourier's law. And we know that Fourier's law states that the heat flux is directly related to the -1 times the thermal conductivity multiplied by the temperature gradient. Now, just like how and so once again, let's try and break these down into what units they're in. So for the heat flux, we have joules times meters per second. So let's try and break these down into what terms they currently are. So for the purple, for heat flux, we have joules, which is energy, because we know this can move as it is a type of energy. And how it's moving is in meters squared per second, is related to the force negative. However, the heat thermal conductivity is in joules times or divided by meters per Kelvin per second. And then the sorry. And then the rate, the temp, and then the temperature gradient is in Kelvin meters. And then the temperature gradient is in Kelvin. So and another way that we are going to relate this is with density once again, which is in kilograms meters cubed. And we are going to also manipulate this equation by the heat capacity. Which is in joules per kilogram per kilogram times Kelvin. So the way once again that we're going to manipulate this is multiply the temperature gradient, so whatever gradient we have, by both the density and the heat capacity. And we're going to do the inverse. And we are going to divide by both of those factors. So let's take a look first at this product. So we have dt x, and this is going to have units of Kelvin. And we're just going to multiply straight across. We get kilograms, meters cubed for density, and we have joules, kilograms per Kelvin. So we are going to cancel out the kelvins, so the kilograms, and we are left in terms of joules our energy. divided by volume, which is our heat gradient. And now let's take a look at the thermal conductivity. Joules, meters, Kelvin, second. And then divided by, so we have meters up top, kilograms, and we have kilograms per Kelvin divided by joules. We're going to cancel out our products, and we are left with meters squared per second. This is going to be our thermo.
Okay, a little bit of a change of scenery. However, we're back. So this thermal diffusivity has the character alpha, and that is the rate at which heat travels through based off of the material. So if I were to have a metal rod and I were to stick it in different substances, how quickly the heat would travel to my hand and burn me. So here we have just shown the two diffusivities, and we both use two different equations and found that through their concentration and their units, we are able to find that they do have the same diffusivity in terms of meters squared per second. Well, the same units, sorry. So now if we were to compare heat and momentum flux with mass, it's actually very similar to the first time that we did it with momentum. So I am going to show you a side-by-side comparison. So for mass, we are going to use the mass flux equation, which is represented by J is equal to the diffusivity coefficient multiplied by the rate of concentration. And once again, these are actually a little bit easier in terms of units. Okay, so these units for mass flux are moles by meters squared per second. For J, the diffusivity constant, or coefficient, sorry, is in terms of moles per, sorry, is in terms of meters squared per second. And the units for the concentration are moles meters cubed times meters again. So you can see right here very easily, we already have the diffusivity coefficient is already in terms of meters squared per second. And that's how we're able to relate all three equations using diffusivity. Okay, so for heat, we were able to relate it using Fourier's law. So now I would like to shy away from this analogy and I would like to look a little more into Fourier's law. Okay, so as we know, it is the heat flux multiplied by a -1 times the thermal conductivity times the diffusion or the temperature gradient. So we're going to talk about why this negative sign is so important. If we have a normal positive graph when we talk about temperature, we have position increasing this way, positive, and we have temperature increasing this way is positive. If we move from one position, so we move from one position to a second position, and we say that we are moving up in temperature. Well, this isn't exactly true. As we know, heat follows a gradient from high temperatures to low temperatures. As such, this slope would be a positive slope. That would suggest that we're actually moving from low temperatures to high, which is so not the case. Instead, the slope has to be negative based off of the assumptions that we are moving in this direction. So the slope has to point from areas of high concentration to low concentration to give you a negative slope and would match how we know how temperature and heat diffuses along a gradient. Let me show you a better image. So if we go from 1 meter to 2 meter and say this is 100 Celsius and this is 200, that would kind of show you that we need to go from a high temperature to a low temperature because heat flows from high to low. Okay, so this is an overview of what we've talked about today. We were able to relate heat, momentum, and mass through a flux analogy. We showed how far a material or a physical property can travel is multiplied by how long. And we showed that how far is the concentration gradient multiplied by the diffusivity. We found that in all three of heat, momentum, and mass, we are able to look through and manipulate the equations and go through the units to be able to find that diffusivity is always in meters squared per second. We found that we talked about diffusivity, and we discussed about the necessary negative sign in front of the thermal conductivity sign K in Fourier's law, because it needs to reflect that heat transfers or heat moves from areas of high concentration to low concentration. And this is my first YouTube video. I hope that it was enlightening. If you have any questions, you can leave them down below. I would definitely like to say that